We must be live now.
Yeah, we are live now.
Okay, thank you very much, Mohammed. And thank you everyone for joining a new Safari Live seminar. Today is my pleasure to introduce Christina Giannoula. She is going to be the speaker. Christina is working as a senior researcher at the National Technical University of Athens. She recently graduated, got her Ph.D. from there, supervised by Professors Gomas, Kosiris, and Mutlu. She is also a collaborator for a long time of the Safari Research Group at ETH Zurich, the group that Professor Mutlu leads. And her research interests are in the intersection of computer architecture and high-performance computing. And specifically, her research focuses on hardware-software co-design for applications, in particular irregular applications with modern computing paradigms such as large-scale multi-core systems and near data processing. Christina will be joining University of Toronto as a postdoctoral researcher in 2023. Thank you very much, Christina. Welcome again to this Safari Live seminar. And now the stage is yours.
Hi, everyone. Hi, Juan. Thank you for the very nice and kind introduction. So first of all, I would like to thank Professor Mutlu and the Safari Research Group for inviting me for this talk today. This is an extended talk of my PhD thesis oral, and it's my first official talk as a doctor in engineering. And for this reason, I'm very excited, and I'm very happy to be giving this talk in the Safari Research Group because the opportunities and the feedback and the discussion that I had with the members of this group, they are the key and the cornerstone to my PhD research and my PhD graduation. And I'm very grateful to my advisor, Professor Mutlu, for his generous guidance and continuous support. His motivation and his passion for high quality teaching and research, they constitute a huge inspiration for me, and they have significantly shaped my research mindset and research personality. So thank you so much for having me today here. So feel free to interrupt me if you have questions during the presentation, and also I'm very happy to take more questions at the end of this talk. Today, we will discuss how to accelerate irregular applications in modern computing systems, and we will mainly focus on CPU and processing memory systems. Irregular applications lie at the heart of many important fields, including graph analytics, neural networks, medical imaging, and therefore accelerating the execution of such applications is of vital importance. In my PhD research, we identify three important characteristics of irregular applications that highly affect their performance. First, irregular applications exhibit inherent imbalance. This means that the objects involved in the underlying data structures are not of equal size. For example, in a sparse matrix vector multiplication kernel, the number of non-zero elements per row or per column significantly varies across rows or columns of a sparse matrix. Second, irregular applications have random memory access patterns. This means that their memory accesses are not sequential, they are not strided, while they are highly affected by the particular input given. These complex memory access patterns are very hard to predict, and they cause poor data locality and complex data dependencies during runtime. And third, irregular applications have low operational intensity. This means that the amounts of useful arithmetic operations performed by the processors over the amount of necessary data to perform these operations is very low, and as a result, irregular applications are severely limited by the available memory bandwidth and the latency access cost in the system. And these three characteristics result in two main performance challenges in multi-threaded executions of irregular applications. Due to inherent imbalance around the memory access patterns, if we use a coarse-grained approach to parallelize irregular applications, we have very high computation and load imbalance among parallel threads with high performance costs. For example, in the sparse matrix vector multiplication kernel, if we equally distribute the rows of a sparse matrix among parallel threads, we have very high non-zero element imbalance and computation imbalance among parallel threads, and we have very high performance overheads. And as a result, we typically use a fine-grained approach to parallelize these irregular workloads. However, with the fine-grained approach, we have very frequent data synchronization and synchronization among the parallel threads, and as a result, a large amount of cycles in processor is spent on synchronization, causing high performance costs. And second, due to the random memory accesses and the low operational intensity, these irregular workloads have high memory intensity, and a large fraction of the application's execution time is spent on data accesses and or waiting for the data to be transferred between main memory and processors. And these data access costs become even worse in modern computing systems, which are typically non-uniform and heterogeneous. Therefore, moving forward, we argue that both hardware components and parallel algorithms need to consider the synchronization scheme and the management of the data as the two major priorities to efficiently execute emerging irregular applications. Low overhead synchronization techniques can enable high load balance, can significantly improve the inter-thread communication, and can expose high levels of parallelism. At the same time, efficient data access techniques and data management techniques can improve the latency access cost of the data and can effectively exploit the available memory bandwidth in the system. To this end, we provide evidence for the following research statement. Low overhead synchronization approaches in cooperation with well-crafted data access techniques can significantly improve performance and energy efficiency of emerging irregular applications. As a result, in my PhD research, I worked both with processor-centric CPU architectures with a deep cache hierarchy and high computation capabilities, and also with memory-centric processing memory architectures that include lightweight processors inside the memory modules and perform computation very close to where the application data resides. The goal of my PhD research is to provide directions and bridge the gap between the processor-centric and the memory-centric computing paradigms in the context of the very important yet difficult to accelerate irregular applications. So next, I will present the 4 key research contributions related with my PhD research. First, I will describe ColorTM, which is a new algorithmic design for the graph coloring kernel tailored for CPU systems. Second, I will present Smart by Q, which is an adaptive concurrent priority queue tailored for NUMA CPU systems. Third, I will describe Synchron, which is a practical hardware mechanism for early-stage processing memory architectures to enable efficient synchronization in processing memory architectures. And finally, I will present Sparse P, which is the first sparse matrix vector multiplication library for real near-bank processing memory architectures. So I will start with my first research contribution, and this is an algorithmic technique that aims to trade off using synchronization in order to have lower data access costs. So the graph coloring problem colors the vertices of the graph such that no two adjacent vertices have the same color. Its most important application is the chromatic scheduling. In the chromatic scheduling, after we color the whole graph, the vertices of the same color constitute independent tasks, independent processes that can be executed in parallel. And with the chromatic scheduling approach, we can parallelize many other graph processing applications like the PageRank, the community detection, and we do not need to use data synchronization. We don't need to use logs or mutexes. The goal of this research contribution is to accelerate the graph coloring kernel in CPU architectures. First, we have examined prior works that they propose parallel algorithms in order to efficiently execute the graph coloring kernel. And then by looking at these prior works, we find that there are three main steps, three main approaches. They follow three main steps. In the first step, all threads speculatively color the whole graph without using locks, without using synchronization. So in the first step, we need to transfer the whole graph from main memory to processor in order to traverse all the edges and speculatively assign color to the vertices. In the second step, the threads iterate over the whole graph again in order to detect coloring conflicts, coloring inconsistencies that have been appeared in the first step. Since in the first step we didn't use locks and synchronization, we might have adjacent vertices with the same color. So again, for the second step, again, all the threads need to traverse the whole graph. And we need, again, to transfer the whole graph from main memory to processor in order to find if there are coloring inconsistencies, coloring conflicts. We assume that the graphs are very large and they cannot fit in the last level cache. So in the second step, again, we need to access all the data in the whole graph from main memory. And there is a final third step where either only one sequential thread, only one single thread resolves the coloring inconsistency, resolves the coloring conflicts and assigns new colors to the conflicted vertices. Or the steps 1 and 2 are repeated multiple times in a multi-threaded context using multiple threads, and they are repeated multiple times until we find a valid coloring for the whole graph. And we name these prior works lazy coloring approaches because they detect and resolve the coloring conflicts lazily. They detect and resolve the coloring conflicts much later in the runtime compared to the time that the coloring conflict appears. We need to traverse the whole graph to speculatively color all the vertices, and after that traversal, we go again over the whole graph to identify if there are conflicted vertices. And as a result, the conflicted vertices are accessed multiple times lazily. This means that they are accessed using the main memory with a very high probability. So overall, these prior approaches, even though they do not use synchronization, they do not use locks and mutaxes, they cause very high data access costs because they need to traverse the whole graph at least 2 times, and they access the conflicted vertices multiple times lazily, meaning that they are accessing the conflicted vertices with using the main memory with a very high probability. To resolve the high data access cost of prior works, we propose a new algorithmic technique which is called color TM. The color TM trades off using synchronization with lower data access costs. We do use synchronization, a lightweight synchronization scheme, but we enable lower data access costs in order to slightly increase the synchronization cost, but we significantly decrease the data access costs. And color TM is based on 2 key ideas. The first key idea is that we enable an eager conflict detection and conflict resolution approach. So color TM eagerly detects the coloring inconsistencies at the time that they appear. It repeatedly iterates on each particular vertex until a valid coloring is found. This means that we access the conflicted vertices multiple times, however, using the low-cost on-chip caches with a very high probability. And with the eager recoloring idea, we minimize the data access cost and the latency access cost. And second, since we do use synchronization, we have proposed a speculative synchronization and computation scheme in order to minimize the synchronization cost. The key idea is that we speculatively perform the computation and the data accesses, most of the data accesses outside the critical section. We find a speculative color, a candidate color for the vertex outside the critical section. And inside the critical section, we have only a few data accesses and a very small validation step. Inside the critical section, we have a validation step where we validate if the speculative color produced outside the critical section is correct and it is still valid. If the validation step fails, we repeatedly iterate to find a new speculative color for the particular vertex with the eager key idea that I explained before. And with this speculative synchronization and computation scheme, we aim to enable very short critical sections with small memory footprint. And as a result, even though we do use synchronization, we have low synchronization costs, and we can expose high amount of parallel. And this is the evaluation of our approach. We compare color TM with the prior lazy coloring approaches across a wide variety of matrices, and we show that color TM significantly outperforms prior approaches across a wide variety of real-world graphs with diverse different characteristics. And we have also extended our proposed technique in order to provide a balanced graph coloring kernel. In the balanced graph coloring kernel, the color classes produced have almost equal sizes. And with this balanced graph coloring, we can provide high resource utilization in real-world applications, and we can improve the load balance in the real-world applications of the graph coloring. We demonstrate that the balanced color TM variant provides very high performance benefit over prior works across a wide variety of real-world graphs. And we also demonstrate that the balanced color TM outperforms the imbalanced variant in a real-world application. In a community detection application, it performs much better. So next, I will present my research contribution, what is called Smart IQ. It was presented at the Computing Frontier Conference in 2019. In this design, we propose a new data structure, an adaptive data structure that dynamically switches between two different modes in order to achieve low data access costs in high contention scenarios, and in order to achieve low synchronization costs in low contention scenarios. So let's take a look on this contribution. In this work, we explore the concurrent priority queues, the concurrent priority queue data structure, which is widely used in a variety of real-world applications. One of the most important applications is the Dijkstra algorithm. And we have experimented with prior concurrent data structures, concurrent priority queues in NUMA architectures, in NUMA CPU systems, and we make two key contributions. First, the priority queues exhibit medium contention because in the insert operation, multiple threads work on different elements of the data structure, on different parts of the data structures, and as a result, we have low contention. And the priority queues have a second operation, which is the delete min or the delete max operation. Here I will assume the delete min operation. And in the delete min operation, all threads highly compete to remove the first few elements of the priority queue. And as a result, we have a very high contention scenario. And when we evaluate prior NUMA-aware and NUMA-oblivious concurrent priority queues that have been proposed in the literature, we find that in insert-dominated scenarios where we have low contention, the NUMA-oblivious priority queues achieve higher throughput compared to NUMA-aware designs. However, as the delete min ratio increases, we have we increase the contention in the same elements of the priority queue. And as a result, we find that the NUMA-aware concurrent priority queues proposed in the literature achieve better performance compared to the NUMA-oblivious priority queues. And as a result, our goal in this work is to design an intelligent priority queue to always provide the best performance and the highest throughput under all different contention scenarios, both under high, medium, and low contention. To this end, our contribution in this work is twofold. First, we introduced NADL. NADL is a generic technique to provide, to obtain highly parallel NUMA-aware concurrent data structures. The idea of NADL is that we have designed a wrapper, a framework, that wraps a NUMA-oblivious data structure and transforms it to its NUMA-aware counterpart. And the second key contribution is that we have designed an adaptive priority queue to always perform best under all different contention workloads. The key idea is that the smart PQ that we propose dynamically switches between two modes, a NUMA-aware and a NUMA-oblivious mode, depending on the contention, the current contention that we have in the data structure. And in this way, we aim to we provide the best performance under all different contention scenarios. So next, I will describe these two key contributions. The key idea of NADL is that the operations performed in the data structure are executed by dedicated threads, which are called server threads. And these server threads are located and they are placed in one single NUMA node of the system. In this way, the elements of the data structure remain at the memory hierarchy of one single NUMA node. And as a result, we have designed a NUMA-aware technique because we have very low data access cost to the elements of the data structure. The remaining threads in the system that are running in the system, they are called client threads, and the client threads perform operations by delegating those operations to dedicated server threads. Their server threads modify the data structure, they modify the elements of the data structure, and they give the return value back to the client thread. We use a low-cost communication protocol, which was proposed in SOSP 2017, in order to communicate messages between the server and the client threads. This communication protocol that has been proposed, it minimizes the cache coherence messages, the cache coherence overhead. So the benefits of the NADL technique is that it is a very generic and it is a framework, a general framework that wraps any NUMA-oblivious data structure and transforms it to a NUMA-aware data structure. It minimizes the memory traffic in the system because the data structure remains at the memory hierarchy of one single NUMA node, and it also leverages a low overhead communication protocol among the software threads, among the parallel threads. The downsides of this key technique, of this idea, is that we do need to use logs. We do need to use synchronization because we have multiple server threads that concurrently access and concurrently modify the data structure. And second, the parallelization, the parallelism, the amount of parallelization that we have is limited to the number of the server threads that we locate in one single NUMA node. And it is typically limited by the number of the cores and the processor that we have in one single NUMA node. And our second contribution is that we have designed Smart PQ, an adaptive priority queue that dynamically, that on the fly switches between two modes, a NUMA-aware mode and a NUMA-oblivious mode. So we address two key challenges. The first is to design an adaptive priority queue that switches between the two modes with low synchronization overheads between transitions, with low cost with low cost whenever it switches from the NUMA oblivious to the NUMA aware mode and vice versa. To achieve this, we use NADL and we configure the underlying implementation of NADL to be exactly the same implementation, the same concurrent implementation as the one that we use in the NUMA oblivious mode. This means that the elements of the data structure are accessed using exactly the same way, the same policy in both modes. And this means that the parallel threads that are modifying the data structure, they are synchronizing using exactly the same synchronization scheme, exactly with the same synchronization approach. And by using the same underlying implementation for both modes, for both the NUMA aware and the NUMA oblivious modes, we can switch from one mode to another mode with no need for barrier synchronization. We don't need to use barriers whenever we move from one mode to another mode, and as a result, we have very low synchronization overheads and negligible overheads upon transitions. And the second key challenge is how to switch, when to find whenever we need to switch from the one mode to another. In order to identify which is the best performing mode in a particular time during the execution, we query and we have designed a decision tree classifier that is integrated in the Smart PQ, and we frequently query the classifier in order to predict us, in order to give us which mode we need to use. If we need to use a NUMA aware, a NUMA oblivious, or a neutral mode, if the NUMA aware and the NUMA oblivious modes have almost equal performance. They have similar performance benefits. This decision tree classifier has been designed in order to have very low traversal costs, because we frequently query the classifier during the runtime multiple times, so we need to have very low cost. And also, it has been designed to give us a very high accuracy.
Christina, I would like to ask you something. Can you go to the previous slide?
Yes.
So you said the decision tree classifier can choose between NUMA aware, NUMA oblivious, and neutral. So in the neutral, what is it going to do? Is it going to operate NUMA aware or NUMA oblivious, or? It is,
yes, that's a good question. It operates in the mode that it is right now. If it is in the NUMA oblivious, we keep the NUMA oblivious because they have similar performance. So we don't want to switch to another mode. In order to minimize the overheads of switching, we keep the mode that we have previous. If we have a NUMA oblivious mode and the classifier gives us a neutral, we stay in the NUMA oblivious mode, and we keep with that policy. If we have a NUMA aware mode and the classifier predicts us the neutral, we stay in the NUMA aware mode to avoid the switching.
I see. Okay, that makes sense. Thank you, Christina.
So there is one question in YouTube I'd like to ask, Christina.
Yeah, sure.
Are there any traffic measurement comparison between NUMA nodes or under these two NUMA aware oblivious modes?
I didn't catch the second part of the question. Can you repeat?
So the second part is about under the different NUMA aware or NUMA oblivious mode. I mean, traffic measurement comparison.
Actually, I mean, like you mean like probably the question is like if we have a metric on the traffic apart from the throughput.
Yes.
The speed up.
Yes, I think so.
Actually, no, we don't have any metric on the traffic on the paper right now. We only measure the final throughput that we get.
Okay, thank you, Christina.
Yeah, but I guess that yeah, probably with some profiling tools that could be measured.
Yeah, makes sense. I agree. Thank you.
Okay, thank you too. Is there any other question?
Not for now. I think you can go ahead. Thank you, Christina.
Okay, thank you too. So we have evaluated both NADL. Basically, here I show the evaluation of NADL over prior NUMA oblivious and NUMA aware designs. Prior NUMA oblivious and NUMA aware concurrent priority queues that have been proposed in the literature. And the metric that we use here is throughput, the operations per second that we perform in the data structure in the priority queue. And we find that NADL achieves the highest throughput under high contention scenarios, in scenarios where we have a delete min dominated scenario. Under low contention scenarios, in scenarios where, for example, we have an insert dominated scenario, the Alistair-Herlihy implementation was proposed in PIPOC 2015. The Alistair-Herlihy is a NUMA oblivious design, and it achieves the highest throughput under low contention scenarios. And in our paper, in our evaluation, we demonstrate that Smart PQ achieves the best throughput under all previous NUMA aware and NUMA oblivious priority queues under different contention scenarios. In this figure, I demonstrate an execution scenario where the contention varies during the runtime. This means that during the runtime, we vary the operations, the ratio of the insert and delete min operations that we perform in the data structure. So we have different contention workloads during the runtime. And we find that the Smart PQ achieves the highest throughput, the highest performance, because it dynamically switches between two modes, either the Alistair-Herlihy as the NUMA oblivious mode or NADL as the NUMA aware mode. It dynamically switches to the best performing mode during the runtime, and we conclude that our design achieves the highest throughput under different contention scenarios and even whenever the contention varies during the runtime. So overall, Smart PQ trades off and it selects a NUMA aware mode in order to have low data access cost in high contention scenario, and it selects a NUMA oblivious mode in order to have low synchronization and high levels of parallelism in low contention scenarios. Next, I will move to my third research contribution, which was presented at HPCA 2021. In this hardware design, in contrast to the previous one, where we had both software designs, a parallel algorithm and concurrent data structures, here we have a hardware mechanism. And this hardware mechanism is called Synchron, and it provides lightweight synchronization among cores in PIM architectures, among the processing memory cores. So let's take a look on this mechanism. Recent advances in memory technologies have renewed the interest of processing memory architectures. In these PIM architectures, we have a very low access cost, very low memory access latency, and we have very high memory bandwidth because we place a low power core very close to the main memory. And as a result, these PIM architectures fit very well with the irregular applications that have very random memory access patterns. However, processing memory introduces new system challenges. One of the most important system challenges in the context of irregular applications is how to enable synchronization, efficient synchronization among the PIM cores of the system. In this work, we identify three important characteristics of PIM architectures that necessitate a new approach to support efficient synchronization in these systems. First, typical PIM architectures do not support conventional hardware cache coherence protocols due to their high area and traffic overhead. And as a result, the coherence-based synchronization mechanism, which is the typical approach for CPU systems, cannot be directly applied in PIM architecture. Second, PIM systems typically lack a shared level of cache memory, a shared last level cache, or a shared L2 cache. And a shared level of cache memory could enable a low-cost communication and synchronization among PIM cores. Now that we don't have a shared level of cache memory, we need to enable the communication using the main memory. However, we would have very high performance overheads, very high performance costs. And the second key characteristic is that the PIM systems are typically non-uniform and distributed, in which the inter-unit communication is much more expensive compared to the intra-unit communication. Given the aforementioned architectural characteristics, if we use a synchronization via a shared memory approach, we would need to implement synchronization using the main memory due to the lack of shared level of cache memory and due to the lack of cache coherence protocol. And this would have a very great penalty in performance and energy. And therefore, we design our approach Synchron, building on the message passing synchronization concept. Synchron consists of 4 key techniques that I will describe next. First, we design low-cost hardware units, which are called synchronization engines, and they are used to coordinate synchronization among PIM cores. The PIM cores communicate their requests using 2 new ISA instructions, which are used to assemble a message that is sent through the network from the PIM core to the synchronization engines. And with this idea of the synchronization engines, we eliminate the need for complex cache coherence protocols and expensive atomic operations. And as we demonstrate in our paper, these small synchronization engines have very low hardware costs, very low area and power overhead. The second key idea is that we add inside the synchronization engine a specialized cache memory structure, which is called synchronization table. The synchronization table is a very low-cost cache memory that keeps all information needed to implement synchronization among PIM cores in the system. When a synchronization engine receives a request for a synchronization request for a particular synchronization variable, it directly buffers the request in the synchronization table. It keeps all the information and metadata needed inside a small low-cost cache memory, the synchronization table. And with this key technique, we avoid using main memory for synchronization. We avoid keeping metadata and information in the main memory. And as a result, we minimize the latency access cost for the synchronization variables and to enable a very efficient synchronization. The third key idea is that since the PIM architectures are non-uniform and distributed, we have designed Synchron to organize the communication with a hierarchical manner. For a particular synchronization variable allocated in a PIM unit, the engine that is physically located in the same PIM unit with it is considered as the master synchronization engine. The master synchronization engine is responsible to globally coordinate synchronization for that particular variable. First, PIM cores send their requests to their local synchronization engine located at the same PIM unit with them. And in the next level of communication, the synchronization engines communicate with the master synchronization engine by sending aggregated messages on behalf of all the local PIM cores within their PIM unit. And with this, by sending aggregated messages across the PIM units, we aim to provide, we aim to minimize and reduce the expensive network traffic across the PIM units of the system. And the four key idea is that whenever the hardware synchronization resources are oversubscribed, we use main memory as a fallback solution. We use a programmer transparent technique to handle overflow scenarios. If the proposed synchronization table is fully occupied and it overflows, the master engine issues read and write request to the main memory allocated issues reads and write request to the synchronization variable allocated in the main memory and keeps metadata for synchronization in the main memory. With the integrated overflow management approach, we aim to have low performance degradation in overflow scenarios, and we aim to provide very high programming ease because the overflow scenarios are handled in a programmer transparent manner.
Christina, I have a question here.
Sure.
So I think you said in the previous slide, I think you said that the synchronization engine that operates as the master is the one that is closer to the synchronization variable, right?
Right.
So, however, where the synchronization variable is allocated might have a strong impact on the performance, right? Depending on who accesses and how frequently it is accessed. So did you do any evaluation related to that, or your choice of where to allocate synchronization variables was sort of random or always the same node for all experiments, or how did you evaluate this?
Sure, that's a very nice question. So first of all, I just need to clarify that the master engine is different for a different log, right? Because we have multiple logs, assuming that we have a graph and we have 1 million vertices. In a fine-grained solution, we have 1 million logs, one log associated for a particular vertex. And these logs are allocated across all of the PIM units, the multiple PIM units. So for each log, we have a different engine, which is considered as the master engine for that particular log. In the way that we identify what is the engine that is the master engine is based on the address, the physical address, right? Because based on the physical address, we identify where is allocated the log and what is the corresponding master engine. So we have the address in the messages that we send between the PIM cores and the engines. In our paper, we have used in order to identify the placement and the impact of the placement, we have used a random placement and we compare it with MITIS placement. MITIS is an open source GitHub project that takes a graph and you give the number of the partitions. For example, I have 4 PIM units, so I want to partition the graph in 4 parts. And this software tries to minimize the cross edges across the partitions. It tries to group the vertices in 4 groups, and the MITIS it's an algorithm that predicts the minimum cross edge partitioning. So in our paper we compare the random partitioning and the MITIS partitioning, and actually we demonstrate that. Basically, if we compare Synchron with prior approaches, Synchron still is better even with a random partitioning or the MITIS partitioning, because this is orthogonal to our approach. Even with a better data placement and with a better technique, we can still minimize the synchronization overheads based on our key techniques. And basically, with them, the main key observation that we have is that the utilization in the synchronization tables is lower with a better data placement. Because if we have a random placement, we need to keep in the synchronization tables, we need to keep 2 entries, one in the local engine and one in the master engine. With a better data placement, we have a better utilization in the proposed synchronization tables, because the local engine is also the master engine with a very high probability. So we minimize the traffic across the PIM units, and as a result, we minimize the entries that we need to keep in the table.
Okay, yeah, that sounds very good. Thank you, Christina. I would like to ask you one more thing. Now that we see this slide with this figure, so here the PIM cores could be similar to the DPUs that exist in the admin PIM system, right? And there we know that there are also synchronization mechanisms like mutexes, for example, or locks that you're also evaluating in Synchron. So how would you combine those locks that are internal to each PIM core to locks that are for the entire system or at least for the entire PIM unit? Or you could modify whatever design exists in current admin DPUs, for example, in order to use the synchronization engine in all cases. What do you think it would be more beneficial?
Yeah, I believe that Synchron could be used within the PIM unit, and basically across. I mean, the key idea is that we right now we have like two levels of hierarchical of the hierarchical scheme. We have within the unit and across the PIM units. In a nearbank PIM system like the AppMem, I would extend Synchron to have even like 3 or 4 levels of the hierarchical communication. We would need to have like one engine within the DPU, one engine within the chip, where we have 8 DPUs, and another level of hierarchy for the different teams in the system. And yeah, basically we would need to extend the design to have like multiple levels of hierarchy in that case.
Okay, that sounds good. Thank you, Christina.
Thank you too. Any other question?
So maybe Christina, I have a question here. So about the interconnection network that you assume in the baseline, is that based on I don't know, it's not probably a real system, but do you think this baseline is a reasonable interconnection network?
Yes, that's a very good question. Actually, we use a simulator, and we in our paper, because we have like this feedback for many reviewers. We have a sensitivity study on the latency across the PIM units. So we have yes, we have a sensitivity study where we have a small latency across the PIM units, and we increase it up to a very large amount in order to see the effects. The key observation that we have in that sensitivity study is that if you have a very high latency across the PIM units, this latency dominates the performance, and the synchronization overheads are very small, a very small fraction of the total execution time, because the data access across the PIM units dominate the performance for the actual memory accesses. And in that case, all the synchronization schemes perform similarly. They have very similar performance because the data access across the data access on the real data of the software are the most important part, and they dominate the performance.
Yeah, that makes sense. Yeah, thank you.
Thank you. Okay, so regarding the evaluation of Synchron, we compare Synchron with 3 other schemes. First, Central, which is a centralized design where we have only one dedicated PIM core that coordinates the synchronization among all the remaining PIM cores of the system. And it keeps metadata and information for synchronization using its memory hierarchy, using its private cache and the main memory. And then we have Higher, which is a hierarchical design where one dedicated core per PIM unit, we have one dedicated core per PIM unit that coordinates the synchronization among the PIM cores and keeps metadata for synchronization using its memory hierarchy, the private L1 cache and the main memory. So it's a software-based message passing hierarchical scheme. And we also compare Synchron over ideal, which is an ideal scheme with zero cost for synchronization, with zero overhead for synchronization. It's a very theoretical upper bound. We demonstrate Synchron's benefits across a wide variety of pointer chasing workloads. In our paper, we have like 9 different pointer chasing workloads. Here I demonstrate 3 of them, 3 out of the 9, stack, a hash table, and a linked list. And we find that across a wide variety of contention scenarios, even with a high contention, medium, and low contention scenario, the Synchron provides higher performance benefits over prior software-based message passing schemes proposed in the literature. And we also evaluate the performance of various data analytics, irregular workloads, including graph processing kernels and time series analysis application. And we find that Synchron performs closely to an ideal scheme with zero cost for synchronization for various data analytics and irregular applications. We also demonstrate the system energy achieved using Synchron. We find that Synchron significantly minimizes the network energy because of thanks to its hierarchical protocol, and it also minimizes the memory energy because it uses the synchronization tables to keep metadata for synchronization, and it avoids using main memory, so it also minimizes the memory energy consumption across a wide variety of irregular applications. And lastly, I will describe my latest research contribution, Sparse P, which was presented at Syncmetrics conference the last summer. In this contribution, we have designed an efficient sparse matrix vector multiplication library for real processing memory architectures. And the key techniques that we used is that we aim to minimize the data transfer costs across multiple PIM cores. And we aim to minimize the synchronization costs within the PIM core across multiple threads of a single multi-threaded PIM core. So let's take a look on this contribution. Sparse matrix vector multiplication is a fundamental linear algebra kernel, and in commodity systems like CPUs and GPUs, it has been repeatedly reported to achieve only a small fraction of the peak performance because it is mainly bottlenecked by the bandwidth, by the available memory bandwidth of the system. Recently, we have seen several manufacturers that have commercialized near-bank processing memory systems, near-bank PIM architectures. These PIM architectures can alleviate the memory bottlenecks because they provide a very large aggregate memory bandwidth, and therefore they are a very promising architecture to accelerate the SPMV kernel, the SPMV computational kernel. So real near-bank PIM systems include several PIM DIMMs that are connected through the common memory bus to a host CPU. And each PIM DIMM comprises multiple PIM cores. Each PIM core is very close to a local DRAM bank and can support multiple threads, multiple hardware threads. In this research publication, we make 2 key contributions. First, we designed Sparse P, which is the first open source SPMV library for real near-bank PIM systems. Sparse P supports 25 efficient SPMV kernels tailored for near-bank PIM systems, and we aim to cover a very wide variety of sparse matrices and a very wide variety of real applications of the SPMV. And second, we conduct a comprehensive study of the popular SPMV kernel on the first commercially available real PIM system, the UpMem system. Our characterization study includes comparisons to state-of-the-art CPU and GPU systems and provides many recommendations for software system and hardware designers of PIM systems. Next, I will briefly present some representative results of our characterization study. The end-to-end SPMV execution on a real PIM system can be broken down in 4 steps. First, the time to load the input vector into DRAM banks of the PIM-enabling memory modules. Second, the time to execute the SPMV kernel on PIM cores. Third, the time to retrieve partial results from DRAM banks to the host CPU. These partial results are related with the output vector. And finally, the time to merge partial results in order to assemble the final output vector on the host CPU. This is the end-to-end execution time, the SPMV execution time on a PIM system. And in this analysis, we have omitted the time to load the sparse matrix to the PIM-enabling memory modules because this time is typically hidden. It can be amortized and can be overlapped with other computation on a real-world application of the SPMV. So given that this time to load the sparse matrix is not in the critical path, we omit this overhead from our analysis. In the Sparse P contribution, we have experimented with 2 types of data partition techniques. First, we provide an one partitioning technique where the matrix is horizontally split among the PIM cores. And this is a compute-aware design because the PIM cores directly compute the final elements for the output vector. So we do not have partial results and we do not have the merge step on the host CPU. The 4th step is 0. The complete SPMV execution is performed only using the PIM cores. And second, we have experimented with the 2D partitioning technique where the matrix is partitioned in 2D tiles. The number of tiles is equal to the number of the PIM cores that we use. And this is a data-aware technique because with this approach, we aim to strive a balance between computation and data transfer costs because we transfer a smaller amount of bytes for the input and the output vectors to and from the PIM-enabling memory modules. However, the PIM cores produce partial results for the output vector, and these partial results are transferred and merged in the host CPU in order to assemble the final output vector. As a result, when we compare these 2 techniques, in this experiment we vary the number of PIM cores from 64 to 2,528 PIM cores. And for each matrix, we select the best performing SPMV execution. We keep the SPMV execution with a particular number of PIM cores that gives us the best end-to-end performance, including the data transfers, and this is per matrix. This experiment is per matrix. So when we compare the compute-aware and the data-aware technique, we find that the data-aware 2D partitioning technique performs best in matrices with in relatively regular matrices. In matrices where the disparity of the non-zero elements across the rows and the columns of the matrix is low. However, whenever we have a power law matrix, a power law distribution, a power law non-zero element distribution, the compute-aware technique performs best because it provides it provides better compute balance across the PIM cores. However, across all the matrices, the different matrices, we find that the best performing SPMV execution is achieved using a much smaller number of PIM cores than the available PIM cores of the system. There are many idle PIM cores in the system because the best SPMV execution is a trade-off between computation with lower data transfer costs. And this comes to our first recommendation for software and hardware system designers. We suggest that we need to further improve the data transfer costs in the PIM architectures. For example, by providing hardware support to effectively overlap the computation with the data transfers in the PIM system, to integrate the PIM enabling memory modules as the main memory of the system in order to minimize the load step, the load data transfer cost, and also to design high-speed communication channels and optimized libraries for the data transfers to and from the PIM enabling memory modules.
Okay. Can I ask
Sure.
maybe a couple of questions here? So I think that these recommendations are very interesting. I mean, and clearly necessary according to what you have shown in with the results. However, could you? I mean, you have evaluated the admin system, even though the proposed implementations or the proposed partitioning and synchronization techniques could be applicable to other PIM systems as well, but in particular for the admin system, what prevents the admin system from actually overlapping computation with data transfers, and how would you enable that, if you can illustrate that?
Right, that's a good question. So I think that the key concept is that as we transfer data to the PIM enabling memory modules, concurrently the PIM cores need to operate. They need to perform computations on the data. So in the AppMem system, typically we have two modes. The one mode is the data transfer. The other mode is the computations on the PIM cores. One idea to do this overlapping is that we have different DRAM banks per core, per PIM core, and as we transfer data on the first bank, on the first DRAM bank, the PIM cores can compute and read and write the data from another PIM core, local PIM core, and then in the next step we do the opposite. The PIM cores compute and read data from the second DRAM bank, and we transfer data from the host CPU to the first DRAM bank. So it's like a double buffering technique that we need to enable in the system. And basically we need two buffers, right? So the two buffers are the two different DRAM banks.
Okay. So in that sense, I mean, just one comment is, so seems that you would be able to overlap in proportion to the number of additional banks you would have.
Yeah, that's a trade-off.
Okay, sounds good. You were going to say something else?
No, I'm just saying that it's a very simple design, not to modify the internal circuitry of DRAM too much, right? Because the goal is that we don't need to do some huge modification in the internal circuitry of DRAM.
Okay. Yeah, that makes sense. Another question I have is related to the second point here, integrate PIM enabled memory as main memory of the system. That's also probably, the question is why this AppMem memory is not yet main memory of the system. Are there any fundamental reasons why that's not possible?
I think that this is easier to be implemented with the current hardware infrastructure. Basically, it's like designing modifying the system level, because we need a particular malloc, right? So whenever we do a malloc, we need to malloc data on different banks, or we need to malloc replicated data. So the key idea is that here we have a distributed architecture. So we have a replicated data on each DRAM bank and local copy at each DRAM bank. So in the system level, we need to design a library, a malloc, that whenever we malloc data, we replicate copies and we allocate copies on multiple DRAM banks. I think that this is not a hardware modification. It's basically a system level modification, a software library that needs to be implemented. So it seems easier, and I hope that in the future we will have malloc and free, dedicated malloc and free libraries for distributed near-bank PIM systems.
Yeah, that indeed could be a very nice idea, right? Have some input from the user, from the programmer, to decide when some data is shared or when some data is private and needs to be replicated.
Yeah, we need to design a different API compared to the malloc that we have. We need to give like the particular core that we need to allocate the data. The input argument needs to be like the bank or the core that we want to allocate the data. Yeah, so we need to create a new API for that. But I believe that it's much easier to be added.
Okay, thank you, Christina.
Thank you too. Any other question? Okay, if not,
I don't see any other questions for now in YouTube. Thank you.
Okay, yeah, I will continue. Overall, in this Sparse P contribution until now, we have seen that we implemented some data partition techniques in order to minimize the data transfers across multiple PIM cores. And now we will look at one single PIM core. And within the PIM core, we have shared memory. So the multiple threads, the multiple tasklets, they are called tasklets, but they are basically threads. The multiple parallel threads can see, can read, and can also write the same shared data within the local DRAM bank. In a shared memory model that we have here within the multi-thread PIM core, the major priority that we need to optimize is the synchronization aspect. And as a result, we have explored 3 different synchronization approaches for the SPMV kernel. First, we use a coarse grain approach. We have implemented a coarse grain logging approach where we have one single log, one single mutex to protect all the elements of the output vector. Whenever a thread needs to write, to update an element of the output vector, it needs to acquire this particular log. So we have a very high contentious scenario because all threads highly compete for the same log. Next, we have a fine-grained logging policy, a logging approach, where we have multiple mutexes to protect the elements of the output vector. We have a round-robin policy. Each log protects a subset of the elements of the output vector, and these are consecutive elements. And with this approach, different threads can access they are trying to write different elements of the output vector, might need to acquire different logs, so we have a lower contentious scenario. And finally, we have experimented with a log-free approach in which parallel threads create partial results. These partial results are temporarily stored in a scratchpad memory, and then later, one single thread merges the partial results and assembles the final results and writes the final element of the output vector in the local DRAM bank. So one note here is that threads work on consecutive, each thread works on consecutive rows of the matrix, and as a result we have a small amount of partial results. Basically, the number of partial results is linear with the number of parallel threads that we have. So in this experiment, we evaluate all of these three synchronization approaches using 16 threads of a single multi-thread PIM core. We observe that typically the log-free approach provides better performance compared to the log-based approaches, the coarse grain and the fine grain logging approach. However, the key observation that we do in this experiment is that the fine grain logging approach does not improve the performance over the coarse grain logging approach. Even though we have multiple logs or one single log to protect the output vector, we have the same performance. And this is because inside the critical section, we have memory accesses. Remember that the critical sections always protect shared data, and typically within the critical section, we have writes, we have memory access. All these memory accesses are serialized in the DMA engine of the AppMem system, in the local DMA engine, because they are performed as a transactions to the AppMem PIM hardware. And as a result, the critical sections are serialized. This means that even multiple threads acquire different logs and work on different parts of the data structure. The critical sections are serialized because they include memory accesses, which are performed as transactions in the DMA engine, and as a result, we get the same approach with the fine grain logging scheme as the approach that we have in the coarse grain logging scheme. And this is a very interesting observation, because typically the fine grain logging in CPU architecture provides a much better performance over the coarse grain logging approach. But here we can see that in a PIM system, a fine grain logging scheme might not provide better performance, better results over the coarse grain logging scheme. And this enables the second recommendation that we do in our paper, and it's basically for hardware architects of the PIM systems, that we need to provide low-code synchronization support, and we need to enable multiple concurrent memory accesses to the local DRAM bank. And one suggestion that we do, I already mentioned this suggestion as in the previous question. One suggestion that we do is that we use multiple DRAM banks per multi-threaded PIM cores, and we have 2 DMA engines for each bank. So in this design, we expect that we double the amount of parallels that we can expose in the critical section, because multiple threads that work on different elements of the data structure and they acquire different logs might be parallelized if the right updates on the elements of the output vector are located on different the elements are located on different DRAM banks. And yeah, this design can also help the double buffering approach in the data transfers, and also it can enable very low-cost synchronization, and can enable a high level of parallelism within the PIM core.
Mm-hmm. So it's interesting that the same solution could solve both issues. One question I have while looking at this picture is these 2 DMA engines are going to be moving data between the DRAM bank and the WRAM, right? The scratchpad memory of the PIM core. In that sense, would they need to synchronize with each other in some way, or coordinate, or how would that be handled?
The question is how,
because they both may. Yeah, so the question is because these two DMA engines will be moving data to the scratchpad at the same time, how will they synchronize in order to not overlap at this and yeah, maybe even overwrite at some point. So
yeah, I think that the scratchpad memory operates also it should be operate like the programmer particularly defines where in the scratchpad memory we put the data. So assuming that we have two different threads that working on two different DRAM banks operating on different DMA engine, if the programmer particularly defines where to put the data on the scratchpad memory, we won't have any issue, right? Because it's like the programmer's responsibility not to overwrite data across parallel threads.
I see. Yeah, maybe some small buffer would be needed to have the two engines writing at different cycles, right? If it happens that both transfers occur at the same time or access.
I agree. But I believe that the scratchpad memory, the WRAM in the AppMem should be same, right? I wouldn't do two different scratchpad memory for the two different DRAM banks. I would assume that a common scratchpad memory would work without any issue. The issue would be in the programmer part. I guess the programmability would be worse. But yeah, I think right now in that case we might not need to do partitioning on the scratchpad memory. It would be good to have some shared memory design to do some software tricks there.
I agree. That makes sense.
And,
thank you, Christina.
Sure.
Yeah, go ahead.
And actually, I'm just saying that I think that this in the next level of the AppMem, they will integrate to multiple banks per PIM core. And yeah, I think that's a very reasonable design, and we have observed the need for this design in our papers.
Yeah, it will be very good to reevaluate your strategies.
Yeah.
Whenever we have access to the new systems.
Okay, sounds good. Any other question? Okay, and next I will briefly compare the SPMV execution on the AppMem system with that of a common CPU system and a GPU system. In the GPU system, we also account for the time to transfer one instance, only one copy of the input vector from the host CPU, from the main memory to the GPU global memory. And after the kernel execution on the GPU cores, we also account for the time to retrieve the final output vector to the host CPU. The common CPU systems and GPU systems are processor-centric systems with very high computation capabilities, while PIM systems are memory-centric systems in which we have very high bandwidth capabilities, very low computation capabilities. If we compare the same kernel execution on those two different systems, we find that the SPMV kernel execution on a real PIM system achieves a much higher fraction of the available peak performance compared to that of the CPU and the GPU systems. This means that we have much higher hardware resource utilization, and this means that we have a better cost of ownership, a better financial cost, because we have a particular software kernel, SPMV, that fits better with the underlying hardware. Regarding the end-to-end SPMV execution, we find that the CPU system achieves the highest throughput, the best performance compared to the GPU and the PIM, because we don't have data transfers at all for the input and the output vector. And regarding the energy, we only measure the kernel energy achieved only for the actual SPMV execution, and we find that the SPMV kernel execution on a real PIM system can provide larger energy savings over the CPU system. So until now, we have demonstrated that we can use new efficient synchronization and data management techniques, and we can provide very high performance and energy efficiency in the very important yet difficult irregular applications, irregular workload. So next, I will I mean, I can stop here and ask if there are any questions until now, and if not, I can summarize my talk.
Okay, I was going to wait until the end, but maybe you can go back a couple of slides to the comparison to CPU and GPU. So here I see, so in the end-to-end comparison, the PIM system seems to be way worse than the CPU and GPU, right? But I see that here in these results, you have used floating point numbers that are not natively supported by the admin system. Is that the reason why?
Yes, so I use the floating point numbers, and also this is the one partition technique, is the compute-aware design. So if I have the 2D partitioning technique, which is the data-aware design, we have a slightly better performance compared to the one that I saw here. We have lower data transfer cost. Still, it is worse than the CPU and the GPUs, but it is slightly higher than the one that we have here. However, in the data-aware 2D partitioning technique, we have a lower peak performance ratio. We don't have 50%. We have because this is the data-aware technique where we trade off the data transfer with the computation. We have a lower hardware resource utilization in that approach. Yeah, so it's like two different partition techniques, and they fit on different, as I saw in the evaluation, they fit on different groups of matrices. The 1D fits with the irregular, the scale free, and the 2D partition technique fits with the regular matrix.
Yeah, but my question was related to the use of floating point numbers. So how these would look like if you use integers?
Yeah, so the end-to-end partitioning technique, the end-to-end evaluation, I assume that it will be more or less the same, because the reason that why we have a very low performance is the data transfer cost.
Oh, okay, it's because of the data transfer, right? Because
yes.
Here you are including exactly end-to-end, including everything. I see. So the dominant term is always the data transfer.
Yeah, the integers would be related with the kernel only evaluation that I saw, where I would assume that the available peak performance in integers would be higher than the 4.66 that I saw there, because we have integers implemented on the hardware. So we would have a higher theoretical peak performance on the PIM course. And in that case, we might have a lower percentage on the SPMV execution. Yeah.
Okay, thank you, Christina.
Any other question?
I don't see questions in YouTube. I don't know if there are other questions from someone else in the audience. Okay, maybe later you can continue, I guess. Thank you.
Okay. So next I will recap my talk, and I will recap the seminar talk today. So we find that irregular applications exhibit inherent imbalance, random memory access patterns, low operational intensity, and these particular characteristics highly affect their performance in multi-threaded executions. Therefore, in my PhD research, we argue that lightweight synchronization approaches, in comparison with well-crafted data access techniques, data access policies, can significantly improve load balance, the amount of parallelism, the access cost to the data, and can significantly improve performance and energy efficiency of emerging irregular applications. We demonstrate this approach by designing both hardware and software-based schemes for irregular applications. So first, we have experimented with a graph processing kernel on a modern CPU system, and we propose a new algorithmic technique called color TN that trades off using synchronization in order to achieve lower data transfer, data access costs to the graph data. As the time passes, we have also seen NUMA CPU architectures that were introduced in order to provide higher bandwidth compared to the UMA CPU architectures. So in the NUMA CPU architecture, we have experimented with a concurrent priority queue. In this Smart PQ contribution, we propose an adaptive approach where we aim to minimize the data access costs in high contention scenarios. We use a NUMA-aware policy in high contention scenarios to minimize the data access costs to the elements of the priority queue. And we adapt to a NUMA-oblivious design in low contention scenarios where threads work on different elements and different parts of the data structure. With the NUMA-oblivious design, we achieve higher amount of parallelism, high levels of parallelism. So we have designed an adaptive priority queue that provides low data access costs under high contention scenario and high levels of parallelism under low contention scenario, and achieves the best throughput under all different contention scenarios during the runtime. So next, very recently, we have seen that processing memory, we have seen a very high interest for processing memory architectures. And first, we saw architectures with a shared memory model, where the PIM cores, all the PIM cores can access the available memory in the system, and they have a shared memory model. The PIM cores are located, for example, in the logic layer of 3D stacked cube. So in early stage PIM architectures, one of the most important challenges to resolve in the context of irregular applications is to enable efficient synchronization. And as a result, we have designed a hardware mechanism, which is called Synchron, and it's particularly tailored for shared memory PIM architectures in order to enable efficient synchronization among PIM cores. And very recently, we have seen several manufacturers that have commercialized near-bank PIM architectures in order to have a distributed memory module with a very large aggregated memory bandwidth. In this architecture, we have picked the sparse matrix vector multiplication kernel, which is one of the most important and the most widely used kernels, especially in the HPC domain. It's a very irregular kernel, memory-bound kernel, and we have provided many techniques to improve the data transfer cost and the synchronization aspect on this particular SPMV kernel, and also our analysis provides many recommendations for future PIM systems. So overall, we hope that the techniques and the methods that we propose and we have presented in this seminar talk can enable new studies and can enable further research to even further accelerate the execution of emerging irregular applications in current and future commodity platforms. To this end, sure.
So Christina, before you move on, yeah, I have a couple of questions here. One is about low operational intensity. So can you provide some reason why irregular application exhibit low operational intensity? Because I can imagine why they have inherent imbalance or random memory accesses, but I'm not sure if that's kind of, you know, a must for them that they have low operational intensity.
I see. Basically, the key idea is the concept is that they need more data and they perform less computation, right? So in order to perform one multiplication, you need to access multiple different data which are irregular. They are not consecutive, so you need to have two different data accesses for one multiplication. If you have a regular kernel, you can have like one transfer for two elements which are consecutive, and you do the multiplication.
Okay. Yeah, I guess, yeah, that makes sense.
Basically, it demonstrates the speed gap between the processor and the memory, and the insight is that the necessary data for a useful operation are higher. We need more data compared to a regular kernel. For the same operation, we need less data.
Yeah. And another question is about Synchron. So in this work, you target data parallel applications, right?
Yes.
So if we want to extend this work to, some kind of, server applications, for example, consider that we have many clients and they provide some queries, and that query should happen can be serviced inside the memory. So there are basically each thread is responsible to service a query. So then, basically the synchronization, the way that you implement the synchronization is that, there is no priority across the threads here, because all of them are working together for one application. But if we have several applications or several processes, how we can extend this work, basically? Or are you planning to extend in that direction?
Yeah, I haven't think of this scenario actually, so I wouldn't say it's it is in my close future plan, near future plan.
Okay, but
yeah,
can you comment on it? I mean, some thoughts? Any thoughts on it?
Yeah, I believe that basically synchronization is related with the data structure that you have. Like you have a shared table. So in both scenarios, you have a shared table that it's accessed by multiple threads or multiple cores. So even though it is like from the same application or it is like from different processes in the system, conceptually it is the same, right? Algorithmically, the concept is exactly the same, because the synchronization is related with the data.
That's right. But what I'm wondering is that basically the logs that you are basically when you want to operate on logs and requests there. So basically, you treated them as the same priority, all of them. So there is.
Yeah. So I mean, in that scenario.
So if we have some priority in some threads, I mean, how we can implement priority in logs, for example,
Oh yes, that was the question. I see. So if you want to implement priority, you need to keep one more information. You need to keep one more metadata, a larger amount of metadata compared to the one that we keep right now in Synchron, because we basically you basically need to keep right now we keep like a FIFO queue, and we serve the request with this queue. If you need to implement different priorities, you need to have like multiple queues, different priority queues. So you need to extend the synchronization table. You need to extend the hardware to include like different queues, like to have a high priority queue and a low priority FIFO queue, and you prioritize the request from the high priority queue. So in order to basically implement one more feature, you need to add more information, and you need to slightly increase the buffers that you have in the hardware.
I see. Yeah, I guess that makes sense. Okay. Okay, and my last question here is about this your work in graph coloring, color TM. So you consider a CPU baseline here. Have you also considered GPU implementation for your algorithm, or?
Yes. Yeah, basically, I was working on hardware transactional memory, which is a feature related with the CPU design. So I haven't considered that. I mean, right in the paper that we also have a color team approach where we use logs. It's a variant of the color team where instead of using hardware transactional memory, we use multiple logs, a fine-grained logging design. So I would assume that this color game variant could work on GPUs, could benefit on GPUs.
Okay. Yeah, thank you, Christina.
Thank you too. Any other questions?
Well, not a question, but maybe just a comment with respect to your answer to the previous question from Mohammed, the priorities, right? You mentioned that you would need different queues with different priorities. At some point, you would need as well some algorithm, some mechanism to control that there is no starvation, for example, from lower priority locks, right? So I guess that could open for sure many possibilities in further research.
Yes, I agree. One comment I have is that we didn't implement all of these features in Synchron because Synchron is a hardware mechanism. So if you want to add priorities and starvation features in the hardware, it increases a lot the area overheads and the financial cost. And this is why we didn't implement all these features in Synchron, because it's based on the hardware. In order to implement priorities and starvation features, one approach would be to implement a wrapper, a software wrapper for Synchron, where in the software we handle the priority queues and the starvation scenarios. And it's a software hardware co-design, particularly to design a particular software wrapper for Synchron. And I believe that would be a better approach instead of implementing everything in the hardware.
Yeah, that makes sense here. When usually the area is constrained, you probably prefer to have more processing elements rather than additional features.
Yeah, that's right. So this is why we need a software hardware co-design, that scenario.
I agree.
Okay.
So there is also one question on YouTube. Have you encountered any work on enforcing privilege boundaries in a PIM-enabled memory? Maybe I can also copy-paste the question here.
Privilege in the sense that we give priorities to the PIM cores, or
yeah, I'm not actually sure.
okay, maybe we can ask for more.
I guess the question is, yeah, I mean, my understanding is that they are asking if you are aware of any studies that have enforced privileges in PIM-enabled memories, like AppMem, for example.
Yeah, a privilege is like that in the sense that we prioritize the PIM core execution, for example, in the sense that the security aspect. What exactly?
So one clarification is that prioritization isn't exactly the same as privilege isolation.
I see. Yeah, I'm not sure if I have seen any prior work. I agree that a prioritization policy, more conceptually, it's the same with a privilege policy, a privilege design. I haven't seen any work, but I assume that both that approaches for prioritization might be the same work with the privilege scenario.
Yeah, but seems like necessary research. Looks like necessary research, right? In a server system where you can have PIM-enabled memory and multiple processes that may want to use the PIM-enabled memory at some point. It would be good to see what to do in these cases, right? In case there are some workloads that have a higher privilege or that you need to prioritize. I think that would be important to analyze, especially because kernels might run, they are coarse-grained computation of loading, right? And they may run for several milliseconds at least. That would make that other workloads, maybe with higher privilege, need to stop and need to wait. So I think there is interesting work there. Yeah, I think that that this person agrees. It's necessary before we get mainstream adoption of PIM on desktop and servers. So I guess
that's an important aspect that we need to consider.
Okay, thank you, Christina.
Okay, so finally, I can briefly describe a few future research directions related with the designs that we have seen so far. So one important research direction is that, as we have seen in our characterization study, the irregular applications have a fourth key characteristic. They have a very varying behavior during the runtime. We demonstrate that in a concurrent priority queue, we need to have like an adaptive approach to handle different scenarios. And also we have seen that graph processing kernels also have varying behavior during the runtime. In the graph processing kernels where we typically initialize the data structures that we aim to use, the workload tends to be latency bound. It tends to be bandwidth bound in the initialization step, while in the part where we perform the actual computation of the kernel, the workload tends to be latency bound. So we have a varying behavior from bandwidth bound to a latency bound behavior during the runtime. And one important research direction is that we need to design adaptive algorithmic designs, adaptive parallel algorithms, adaptive runtime system, and hardware mechanisms for irregular application in order to even further accelerate their performance and their execution. A second research direction is that I have explored these irregular applications mainly in CPU and in near data processing architectures. However, there are many other new and unconventional systems like the hybrid system, heterogeneous systems, where we have multiple types of memory and SSD, and also we have disk or persistent memory. So an important research direction is how to optimize and accelerate these irregular applications that access a very large amount of data, very large volumes of data, in new unconventional systems, how to find and propose hot page selection schemes, hot page placement across multiple types of memory, including DRAM and also non-volatile memory technologies, and how to select the granularity of moving data in those unconventional systems, because in heterogeneous and hybrid systems, we can access data in page granularity. We can also have byte addressable memories. So how we select the granularity. And a very interesting direction is to design an adaptive approach that dynamically we select the granularity and we choose between bytes and pages during the runtime based on the needs, the runtime needs of the workload. And in the end, I believe that there are many key insights and many recommendations in this talk, and also in my in my full PhD thesis text, where we can leverage in order to improve multiple aspects of CPU and PIM hardware and software. For example, the graph coloring technique can also be used on graph neural networks, on machine learning application, the graph neural networks. We can leverage the graph coloring in order to identify layers and operators that are independent with each other, and they can be processed and they can be executed in parallel with no need for synchronization between the different layers. So we believe that there are many methods and many techniques that can be leveraged to further improve the software and the hardware. So this concludes my talk. Thank you so much for your attention. I'm very happy to take more questions.
Thank you very much, Christina. Great talk. I wanted to ask you quickly something related to the previous slide. So how are you going to design all these adaptive approaches or all this dynamic behavior in your system? Maybe machine learning techniques can help?
Yeah, actually, I really enjoyed the Sibyl, which is like from the Safari group. It is a design that captures the runtime, the variable runtime behavior that we have in the current workloads, in emerging workloads, and it proposes a machine learning technique for the hot page placement, data placement, basically in hybrid memory systems. Yeah, so I'm not saying that machine learning is like a best fit for everything. It sounds like a very good fit for proposing adaptive designs that we do need them nowadays. But I believe that maybe some simple heuristics, decision trees, or like some simple heuristics might also work to implement adaptive approach apart from machine learning.
Yeah, I agree. ML is very promising. RL is very promising for these kind of problems, but I agree that wherever you can use a simpler heuristic might be faster if it's good enough.
Yes, accurate enough. Yeah.
Okay. Yeah, thank you very much, Christina. Any other questions from the audience? Because I don't see questions.
I think
now in YouTube.
maybe I'll ask one question. Christina, thanks for the talk. It was excellent as usual. I could ask many questions, but I'll limit it to one related to your talk, I think. So I think it's good to have synchronization mechanisms for near data processing. That's great. It comes with an overhead. Have you thought about how to extend irregular application support, both synchronization and other mechanisms for processing using memory, more analog computation type of mechanisms in memory, like Ambit, SIMD-RAM, and maybe even machine learning accelerators going forward that use non-volatile memories, because they have a different model and less of computation.
Yeah, so conceptually, it is like in the near data processing design, you have a core that operates on a larger amount of data. In the processing using memory techniques, you have a core that operates in a smaller amount of data. So assuming that you have a smaller amount of data, you have a smaller amount of synchronization that you might need. In those designs, what I typically say in students as well is that synchronization means communication. So you have like a shared memory design and a large amount of data, you have like this concept of synchronization. If you have a distributed memory module where the cores operate on local data and you have multiple partitions, then synchronization is communication. So you can think of the communication across the processing units, across the different partitions that you have in the system. So algorithmically, conceptually, you can use the same techniques and the same approaches in order to implement efficient communication across the processing units that you have. So I assume that in processing using overall, I assume that in processing using memory approaches, some of the techniques that we propose in Synchron can be translated in the communication efficient design.
Mm-hmm. Yeah, I think it makes sense. I agree. But I think a lot of these processing using memory approaches suffer from irregular applications also, right, to begin with. even without the sync.
Yeah,
mainly
basically,
because of communication.
yeah, basically, it is like this design is also fits very well with embarrassingly parallel architectures, not with the irregular application. So irregular application will always be a challenge to how to accelerate because it is very weird that we have designed these processing memory architectures to provide higher bandwidth and resolve the challenges that we have in the irregular applications. But even in those architectures, we still have high important challenges that we need to resolve. We have high data transfer costs that we need to resolve them in the irregular applications. So I believe that this particular class of application will always be a headache to tackle and deal with that in also in future architectures that might be different.
Yeah, I agree. And I think probably a combination of processing using memory and processing near memory is needed if you really want to handle them efficiently. And also exploit the analog operational properties of memory to do massively parallel computation. And there, I think you can add synchronization mechanisms in the near memory part probably more easily.
Yeah, I guess that it's a part of the heterogeneity trend that we have nowadays in the computer architecture design.
Yeah, I agree. Well, one related question, well, not exactly related, but I think there's some relation also. So apart from synchronization, coherence could be a challenge, especially when you partition these irregular applications across heterogeneous units, right? Do you have any thoughts on how you can design more efficient coherence mechanisms?
For processing memory or processing using memory designs, right?
Yeah, either one, basically. I know you haven't dealt with that in the Synchron work or in the Sparse P work, but it'd be good to get your thoughts.
Yeah, I believe that conceptually the coherence protocol is related with the communication and the synchronization aspect, because in the coherence protocol we need to keep the data up to date. You have multiple replicas and you need to have like both replicas to be consistent. So in the end, it is related with the communication part. Yeah, so I assume that a hierarchical approach that we have in Synchron could benefit like optimize the communication aspect in those approaches. So I assume basically that hierarchical coherence protocols that might have been proposed for CPU systems can be adapted and extended to be applied to apply in processing memory and processing using memory architectures.
Yeah, that makes sense, especially if you want to have coherence on the PIM part. I think the difficulty becomes when you have CPU, GPU, and PIM, and they start communicating with each other. So there's more work to be done in this area, I think,
yes.
to expand the domain of coherence and also domain of synchronization, I think.
Yeah, I agree. But I also believe that the solution might be simpler, right? Because we can just simply think that we have a highly heterogeneous system. So the solution probably is a multiple level hierarchical communication aspect, like having a hierarchical scheme with multiple levels of hierarchical communication.
Okay, yeah, I don't have anything else. Thanks.
Thank you.
I'll pass it back to Juan.
Thank you, Honor. Thank you for the questions and all comments. Okay, yeah, are there any other questions? I don't have any other question myself.
I also don't have any question. There is also no question on YouTube.
On YouTube.
Yeah.
Okay, sounds good. Thank you very much, Mohammed. So thank you so much again, Christina, for the great talk. I hope you continue with your successful research, and I also hope that you will have a very good arrival at your new group in winter 2023. And I also hope to keep in touch with you and continue collaborating.
Sure, definitely we will continue working together. I really enjoy working with the group. I learned too many things, and I like the research we are doing. Thank you for the invitation today.
Yeah, sure. Thank you very much, Christina. And thank you everyone for attending today's Safari Live seminar. Don't miss the next one. And yeah, have a very good evening. Bye-bye.
Bye.